Well, good morning. This is 8:08 on Monday, the 24th of April, 2017, the first day of the last week of class for spring term 2017. And right now it's Math 237, linear algebra. I'm sitting in the room by myself. There's no students here. And this is the last week of classes, like I said. It's the last, let's see, this class has already turned in all this paper, so that's good. Just wanted to remind you, though, one person hasn't turned in test 1, and one person hasn't turned in test 2. And I don't think anyone's turned in test 3 yet. So anyway, please get those in, and on Wednesday I will be giving you the test for what we cover in Chapter 4. We're going to cover Chapter 4 today and Wednesday. Whatever we cover, it won't be a whole lot, but whatever we do cover, that will be your last test. You can think of it, I mean, it is the final exam because it's the last test, final meaning last, but it's not going to be comprehensive. It will just be on Chapter 4 material. So, I don't know of any other major announcements, so without further ado, let's go on and get started from where we left off. And I believe, if I'm not mistaken, we exactly finished Chapter 3 last time, and we're going to start today on Chapter 4, which is vector spaces. Now, vector spaces in one sense is sort of a new idea, but on another sense it's something we've been building toward all along, so it's not totally new. There are a bunch of sections, 8 sections here in Chapter 4. Obviously we're not going to get to probably more than 2 of them, but let's at least get started in 4.1. Okay, hopefully you have hit vectors in some other course somewhere in the past, but in case you haven't, let's go over quickly what vectors are. 4.1 is vectors in Rn. Now, what does Rn mean? That's a space of dimension n. Okay, a single line is a one-dimensional structure. Okay, it only goes one direction. You might say front and back, or right and left, or up and down, or positive and negative, or something like that. But it only has, everything is on that one line, and everything is defined by a single variable. Okay. If it's a horizontal line, that would be x. If it's a vertical line, it would be y. If it's any other dimension of a line, you can name it anything you want it to. And you can name x and y anything you want it to. So that's a one-dimensional construct. Okay? A plane, on the other hand, is a two-dimensional construct. 2 dimensions, you have length and you have width, or you have height and you have horizontal extent, horizontal, vertical. You have 2 dimensions for a plane. So that would represent R2. Doesn't have to be the plane like the board or the floor or the ceiling or a wall. It could be a plane that cuts diagonally across, or any kind of way across space, but everything is defined by the 2 dimensions. Okay, so that would be R2. 3-dimensional space is where we live. 2-dimensional space is where we project onto, you know, the whiteboard or whatever. The 3-dimensional space is where we live. We have length, width, and height, so that would be 3-dimensional space, R3. Okay? Now, in vector algebra, especially since you can come up with constructs and imagination, there is no such thing that I can think of as 4 space. Now, some people like to say, put time in there and with 3 space and you have 4-dimensional space. That's kind of a stretch. It's not a physical space. It's again, a mental or a construct of what R4 would be. But it doesn't have to be that. It could be anything. Now, let's take, for instance, popular topic climate or climate change or something like that. If you were going to study the climate, and I've seen people do things such as this, and you say, what defines the climate? Well, certainly you have 3-dimensional space here on the surface of the Earth, or you might choose your three-dimensional space to be spherical coordinates, because our atmosphere, it follows that more closely than it does a XYZ rectangular coordinate system. If you're talking about a big scale. Small scale, it wouldn't really matter. Big scale, that might be better, but it's still three-dimensional space. But then you might also talk about temperature as an independent variable. You might talk about density as an independent variable. You might talk about gravitational force as a vector force. You might talk about, lots of other things, wind, speeds, velocities, directions. So that would be a vector quantity. A pressure regime, that also contributes to climate. So I mean, you might have right there enumerated between 5 and 10 independent variables. So in order to build a construct to talk about those, you would need 5 to 10 dimensional space. Not space as we understand it, three-dimensional space, but a space R to the n. So anyway, enough of that. Let's move on to. So let's talk first about vectors in the plane. Go back to two-space, XY plane, okay? If you're following in your book, the first figure, figure 4.1, shows this. In physics and engineering, a vector is characterized by two quantities. One is its magnitude or length. There is another word for it that we'll hit a little bit later, but just to keep from muddying the water, we'll just do magnitude or length. And then also its direction. Now, up till now, when you were in scalar math, okay, and you've probably gotten into vector math, but in scalar math, you just have numbers, okay? And you can picture them on a number line, and 3 number lines, 2 number lines, in the plane, XY plane, a horizontal number line X, a vertical number line Y, infinite in both directions. That would be your concept of a plane then, okay? So a vector, though, and on the number line, you just have numbers. So when you have your Cartesian coordinate system, you can pick any point on the plane, and that represents any ordered pair of numbers, okay? But a vector is characterized by both magnitude or length and direction, and it's represented by a directed line segment, okay? Sorry about this, I didn't know that had come up. So what would we mean by that? I'll go on and reproduce, at least somewhatly, the figure that we have here, figure 4.1. So if you have the y direction in this way, x direction in this way. Now obviously I'm only showing the first quadrant of R2, because you see the x can continue on this way negative, y continues that way negative, okay? Understood. But let's say in the first quadrant for now. Let's say we have a vector. Now I don't like the fact that they call this vector vector x. Surely you could get a different name, because they've already identified this as an x coordinate and that's a y coordinate. If you hadn't done that, x would be perfectly fine. But for you to specify some vector up here, okay, as a vector x, I don't care for it. So I'm going to change this slightly and call it vector v. Why not? Vector starts with v, okay? Then this coordinate here would be v1, v2. Now here again, naming it x and x1, x2, you've already named this as x. So basically, your x coordinate here is your, and rather than, this is sort of bizarre, but rather than call that v sub 1, why not call it v sub x? That is the vector v in the x direction, the component of vector v in the x direction, and v2 would then be the component of vector v in the y direction. So call, no, I'm sorry, v sub y. Okay, or y too big. But quite often they're going to call it sub 1 and sub 2. Especially when you get to n space, it'll be sub 1, sub 2, sub 3, sub 4, sub 5, dot, 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 up to sub n. So that's why they're using that. It's a little more precise, but since they named this the x and y axis, don't name the vector that's not on the x-axis x, name it something else, v, okay? And then v1 would be the component on the first axis, which we usually use horizontal first, vertical second, so why not call it v sub x and v sub y? But you get the idea. Different ways you can name it. Now, with this vector, notice it started at the origin, where x and y are both zeros, where your x1, y1, or v1, y1, or vx, vy is 0, 0. That is the point where it started. And it's called the initial point of the vector. This vector up here is called, this point up here, I'm so glad you're here. I hate talking to myself. Okay, Nigel is here. Let's do this. Today being the 24th. Okay, and this Nigel is present. Okay. And as I said before, I can't remember. Yeah, all in this class have turned in the first, and turned in the paper, and 3 of the 4 of you have turned in the first test and second test. So far, I don't have the third test back yet, but get those to me this week if possible. And as I was mentioning earlier, this being the last week of class, this is next to the last day of class for this one, we will, I will give you your test on chapter 4. However far we get today and Wednesday, that'll be your final exam, which will be pretty simple, very short, just covering probably just 2 sections, if that. All right, then let me get set up for you. And those students are here. I don't bother turning on the projector. And I have the lights, so it's easier for me to read, but on chapter 4, section 4.1, page 146. And I know this is old hat to you. I just don't know everyone's background because you've had vectors out the ears probably, okay? This is doing vector spaces, and 4.1 is talking about vectors. So this is pretty much review for you. Okay, so we call the point down here where the vector starts, and here's another Williams coming in. Okay, Marcus is here. Okay, we're on page 146, chapter 4, vector spaces, 4.1, vectors and Rn. And since you've been in physics, you know, you probably dealt with vectors big time already. So this is pretty much a review, but I don't know if everyone in the class is at the same place you are, so when I'm covering 4.1. Okay. And again, everyone's turned in the paper. Both of you have turned in your first and second test. Still need your third test. And on Wednesday, I'll be giving you the last test, which will be the final exam, which will just cover what we cover in 4.1 and 4.2, probably. We'll see how far we get. Okay, and that will be due anytime next week. I don't think there's any special date that I have to have grades in for graduates because we got the whole next week. Y'all aren't in school and we're here, so we got all week to turn them in. So if you have them to me by next Friday, the following Friday, I'll have plenty of time that following week then to get everything in. Okay. So, now, one instructor told me that they had contradictory things on the academic calendar, which is not surprising because what they do, they just copy whatever it was the last year, and then they sometimes forget to take out things they had in there, like there's a faculty duty day listed for next Sunday or something like that. It was a duty day last year when it was a Monday, but this year being a Sunday, it's not a faculty duty day anymore. So they're pretty sloppy with the academic calendar sometimes. Sorry about that. Shouldn't be saying that on Screencast-O-Matic. That'll be published on YouTube for the whole of the world to see and hear. Okay. Anyway, but it's true. Okay. Vectors, again, you're used to this. And I just have a little objection. In their figure 4.1, they named this vector vector x. I thought, fine, if you want to call that vector x, don't call your horizontal axis x, okay? That's using the same letter for two different things that are not the same. So I called it vector v, okay? And then they called the subscripts v1 and v2, which is fine, but since they had already named this the x-axis and the y-axis, why not call that v sub x and v sub y? To me, that makes more sense, and in physics, that's exactly what you do. But in this text, since we won't be dealing just with 3 space, x, y, z space, we'll be dealing with n space, it is more typical. In this book, we'll use sub 1, sub 2, sub 3. But don't call this the x-axis and then name a vector that's not on the x-axis x. Pick another letter. Okay. So here's a vector. It starts at the origin. The initial point is 0, 0. Your v sub 1 or x sub 1 or v sub x, whatever you want to call that, is 0, and so is the y. Your terminal point, that's the other, so this is the initial point, and this is the terminal point. Okay? Terminal point then, now here's the interesting thing. As long as your initial point is 0, 0, your terminal point will have, now we're only doing what, I talked about this before y'all came in, R2, okay? 2 space, a plane. That's what we're talking about here, okay? And we'll extend this to 3 space and then n space later, okay? Now, said all that, and now I can't remember what I was going to. Oh yeah, when you have your initial point at the origin, your terminal point will be at this point. Now, this is a point given by parentheses, v1, v2, x1, x2, vx, vy. Whatever you want to name these, that's going to be your terminal point. Now, in just a little time, we're going to introduce component notation. And I'm sure y'all are conversant with that, familiar with that. Now, I use the same author for pre-calculus algebra and pre-calculus trig. In fact, all of you have had trig, I know. So you've had, well, not everybody's had it here. So I'm thinking everyone's had vectors, but I don't know that for sure. But anyway. This author in the trig book, the pre-calculus algebra trig book, he used for vector component notation angle brackets. And that seems to be the thing that most books are moving toward now. Okay? When we used to say component notation, that was v sub xi plus v sub yj. Those were the component notation. But now they started using just the 2 numbers with angle brackets. But the same author in this book doesn't use angle brackets anymore. He uses parentheses. So the vector v in component notation looks just like the point p, the terminal point p, in ordered pair notation. Exactly the same. So you have to know by the context whether you're talking about the point p in parentheses v1, v2, or later we'll get to vector v, whose components would be, and we used to put angle brackets with them, but now this author in this text puts parentheses around v1, v2, which looks exactly the same, but this is talking about a point, this would be talking about a vector. So again, I'm introducing that now. I shouldn't, but it's not going to be long. Yeah, it's not going to be at all long. In fact, the next paragraph before we get there. Okay? The same ordered pair, v1, v2, used to represent the terminal point also represents the vector. Okay? Now, they again are calling it x. I don't want to call it x because the x-axis is called x. If they hadn't named that as the x-axis and just named it the horizontal axis, then x would have been a perfectly fine thing to call it. But I'm calling it v, so this vector v is, and he uses parentheses, v1, v2. Or you could, if you're in physics, call it Vx and Vy. Now, again, I probably shouldn't bring up physics here, because typically in physics, if you use the symbol V, you're representing a velocity, okay? Not here. This is math. That doesn't indicate it's a velocity. It's just a vector, V. So here's a problem, or a situation. You have the same representation, open parenthesis, V1, comma, V2, close parentheses, for a point and a vector. He doesn't use the angle brackets in this text, even though it's the same author. So anyway, these are called components of the vector V. Now they're calling it vector X, and you can do it whatever you want to. Now, what if you had two vectors in a plane, and these are called U and V. So vector U, and if it's a vector, in the book it's going to be bolded, right? I can't write bold on the screen, so I put the vector symbol over it, okay? But this text uses parentheses. I would have used angle bracket, U1, U2. If you're in two space, we'll name those two dimensions 1 and 2, okay? You have another vector, V, and its components would then be V1 and V2. Now, just a little notice here. The vectors are U and V. The components U1 and U1 and U2, V1 and V2, are not vectors. They are scalars that represent how far out the x-axis, the horizontal axis, the first axis, whatever you want to call that, the component of the first vector goes, and how far up the other axis, the vertical axis, the secondary axis, whatever you want to call that, the vector's component in that direction goes. Those are scalar numbers. They represent, when written in what looks like an ordered pair, but is now a component notation that represents a vector. Now, what would we mean to say these two vectors are equal to each other? Does that mean equal length, equal magnitude? Say again? Okay, that certainly has to be true, but also the other part that has to be true, they've got to be in the same direction. Vectors have both magnitude and direction, so for two vectors to be equal, sure, they've got to have the same length, but this vector and that vector may have the same length, but they're going totally different directions. Totally different, not equal. This vector and that vector, same length and heading in the same direction, they are equal. This vector and that vector, even though same length and in a sense sort of the same type coordinates, because the directions are different, not equal vectors. So that's what's required for them to be true. Both of the components have to be equal. U1 has to equal U2, and U1 has to equal V1, and U2 has to equal V2. Has to. No way around it. They're equal if and only if U1 equal V1, U2 equal V2. Now, the term vector, there's a little blurb in the margin here, derives from the Latin word vectus, I think is how you say that, meaning to carry. The idea is if you were to carry something from the origin to point x1, x2, the trip would be represented by the directed line segment. And that's the other name for this, a directed line segment. Now here's a little bit on that. A line, by definition, is infinite in both directions. That's a line, always. Okay? And a line can be in any direction. Okay? Has no magnitude because it's infinite in both directions. Okay? That's a line. A line segment is a line that's terminal at one end and terminal at the other end. Okay? In other words, it isn't infinite in either direction. Okay? Now, a directed line segment has a direction in it. So a line segment has a fixed length or magnitude, and a directed line segment also has a fixed direction. So that's what makes it a vector. Okay? Forgot to say that before. So let's look at example 1. I'm going to clear the screen for this. And actually what I'm going to do is go to coordinates. Here's a vector u. And this vector u is 2, 3. Okay? It says to represent that vector u, 2, 3, draw a directed line segment, and you tell me how to do this. Okay, yeah, we'll call this the x-axis and this the y-axis. Is that what you said? Okay. Go to the right 2, is that what you said? Up 3, that gives you the point 2, 3. Points are given as ordered pairs in the plane. Ordered pairs in the plane, 2 on the first coordinate, 3 on the second coordinate. Okay, we got that. It's still not a vector though. What would be the vector? From the origin to that point. Okay? Directed line segment. Now, you don't have to put the arrow on the end. I usually do because vectors are directed. In fact, it is a good idea always to do it. Because you could have drawn that same line, but without the arrow on that end, you didn't know that it wasn't going in the other direction. So that tells you that is a terminal point 2, 3. And this vector, they wanted to name it u, so this would be the vector u. And it is a directed line segment. The segment goes from 0, 0 to 2, 3. The direction is from 0, 0 to 2, 3, and that is the representation of the vector. And in this book, they also represent that as open parentheses 2, comma 3, comma, close parentheses. Exactly the same representation as the point. This is the vector. Those are components of the vector, coordinates of a point. Even the names sound alike, so don't get them confused. Okay. Now, what if we were going to represent the vector -1, 2? Vector v is -1, 2. What would we do there? Left 1, up 2. That gives you the point -1, 2. And from the origin up to that, you would have the vector v, which is -1, 2. Same components as the point has coordinates. Okay. Now, they drew about 2 different axes, nothing to keep you from drawing on the same axis. Any questions on that? Pretty simple stuff, right? So let's look at some vector operations we can do. One basic vector, well, what are our operations in scalars? What are those first things you learn to do with numbers? Add, subtract, multiply, and divide. Okay? We're not going to do all those. Okay? We're basically going to start with adding. And then just like, especially after we learned sign numbers, we found out subtraction was just changing the sign of the second number and adding it. So it's actually just like addition, only different. Okay. Vector addition, though, is quite different. Okay. So let me clear all this off the screen so we can deal with vector addition. One basic vector operation is vector addition. To add 2 vectors in the plane, add their corresponding components, period. That's how you do it. They show pictures of parallelograms and things like that. Sure, you can do that, but the easiest way to do it, if you have 2 vectors, u and v, not the same u and v that we had before, okay, and you want to add those 2 vectors, u plus v, then what you do, and by the way, vector u in the plane would be the vector u1, u2, and the vector v in the plane would be v1 and v2. What would be the sum of those two vectors? Also a vector, and what would it be? u1 plus v1, comma, u2 plus v2, close parentheses. That's how you add the vectors. Atom component at a time. Just like the equality of two vectors, the two components have to be identical, okay, in sign, magnitude, and everything. So when you're adding the two, add the first component of one to the first component of the other, comma, add the second component of the one to the second component of the other. Now you have your new vector, the sum vector of those two. And they do show here, without numbers on them, they show a vector u going something like this, and a vector v going something like that, okay? I'm sorry. Goodness gracious. Goodness, I can't get it to come up. There we go. Okay. Try that again. This is vector. Now it won't go away. Okay. This is vector v. Okay? Now, to add those together, the way I've drawn it, u has 1 as its first component. Vector v has 1, 2, 3, 4, 5 as the first component. So the sum of those would be 6. And the y component, or the vertical component, would be 1 for vector v and 1, 2, 3, 4 for vector u. 1 plus 4 would be 5. I've already done that. This would be the sum of those two vectors. Okay? Would be this vector here. Now I drew some other. This is u plus v. I drew some others in there because this is vector u, this is vector v. Now, another thing that we haven't talked about yet, vectors don't have to have the initial point on the origin. If you do not change the magnitude and do not change the direction of a vector, you've got an equivalent vector. So this vector u could be transposed over here. As long as you don't change the magnitude and you don't change the direction, this vector u is the same as that vector u. This vector v is the same as that vector v, as long as you don't change the magnitude or the direction of it. So you can add u plus v this way, and you wind up there. You could add v plus u this way, you still wind up there. That's what the sum of two vectors is. Now, notice, this is a fact, the magnitude of the sum vector is greater than, no, is less than or equal to the sum of the magnitude of these vectors. Okay? Strange but true. You would say that's equal to, not in vectors, because this has a magnitude square root of 5. This one has a square root magnitude of I didn't say that right. Yeah. This has a magnitude 1 plus 16. So that would be square root of 17 would be the magnitude of that vector. This would be square root of 26 would be the magnitude of that vector. Square root of 17, square root of 26. This vector is nowhere close to, well, it's less than or equal to the magnitude of that vector, because if you added this to that, you'd be a much longer line than this. This one, because some of the components add and some of them don't add as completely, then the magnitude of this is always less than some of the magnitudes of those. Okay? Now that's not covered here, but it is the truth, okay? Only time when it's equal if they line up with each other. Magnitude of one plus the magnitude of the other, that would be the magnitude of the sum. Okay, just a little fact that you don't have to deal with yet. But that's how we represent them on, that's called the parallelogram rule, or they have other names for it. The next example, one of the vectors you'll add is also a very special vector, which I find a very annoying vector because it's necessary, that's why we even name it, but it's called the zero vector, okay? And quite often it'll be represented by the number 0, but bold in the book with an arrow on it here. Now in 2 space, what would be the components of the 0 vector? 0, 0. Now we have a problem, Houston. Okay? That problem is this. We defined earlier a vector is a directed line segment, meaning it has a magnitude and a direction. The 0 vector, you might, by a stretch of your imagination, say it has a magnitude of 0. Okay? It has a length which is no length. Okay? It has a magnitude of 0. Okay? So maybe you could get by with this, but what in the world is the direction of that vector? It's not a 0 direction. It has no direction. If it has no length, how can it be pointing anywhere? So this is the one vector that does disobey the formal definition of a vector. It's not a directed line segment because it has 0 magnitude, so it's not even a line segment, and it's not directed because it has no direction. But it's necessary for us to have them because of what we'll see here. Let's look at example 2. And we don't need scalars. I mean, we don't need a graph board to do that. We can just do it here. Find the sum of the vectors. Okay. Here's vector u, 1, 4. And the vector v, -2, or 2, -2. Now, I have to fight myself not to put angle brackets there. When I put them, forget it, ignore me. That's it. What is the sum of these two vectors, u plus v? 3, 2. Oh, I did it. I knew I was going to do it at some point, and I didn't mean to. Imagine that's a parentheses. That's it. Okay? Now, just a little bit of an indication of what I was talking about. The magnitude of this vector is the square root of 17. Magnitude of that one is the square root of 8. Right? Okay? What's the magnitude of this one? Say again? Well, don't. No, I'm just kidding. Square root of 3 squared plus 4, 2 squared. 3 squared is plus is square root of 13, which is a little bit less than the square root of 16. Yeah. Notice here, even though this is the sum of those two vectors, the magnitude of this is actually less than the magnitude of that. Scalars, that wouldn't happen, except if you had negative numbers, and you do have a negative number somewhere in there, so it does happen, but yeah.
I forgot, I'm saying magnitude, but, you know, I forgot how to do it, but then I thought about it. Square root, about 3 squared plus
2 squared. And take a square root of it, yeah, that's it. Okay, now, yeah, the book hasn't gotten there yet. I'm jumping a little ahead because I thought, y'all probably already knew it. So, here's the B one. U is equal to 3, -2, and V is equal to -3, 2. What's the sum of those two vectors? Say again? 0, 0, which we name as the 0 vector. Okay? Pain in the neck. Okay. So, if we think about what the vector u is, which is positive 3 on the horizontal direction, negative 2 in the vertical direction, it's going down like this, right? If you think about vector v there, minus 3 in the horizontal direction plus 2 that one, guess what? Equal vectors in the same line, equal magnitude in the same line, their sum adds to 0. So that's why you get the 0 vector there. And that's why we need to have the 0 vector defined, because otherwise this would not be a closed operation. Now, something else. Let's look at C. We have a u equal to 2, 1, and the v is actually the 0 vector, 0, 0. And what happens if you add these two together? U plus v is equal to 2, 1, which is u. So anytime you add any old vector to the 0 vector, you're going to get the same vector, because you're adding 0 to each of the components, which gives you the same components you had to begin with. So this is a property of the 0 vector. Here they called it v, but they identified it to be the 0 vector. There is your general case. Any vector u added to the 0 vector is still going to be that vector u, because you're adding 0 on x and 0 on y. You're at the same point. Okay. They actually drew these, and you can see those in your text. Another basic vector operation, and by the way, we'll get back to that, is, and we mentioned the 4 operations. Adding and then subtracting is just adding the negative of it. So we'll get to that later. And then the third one was multiplication. Well, there's actually 3 ways you can multiply vectors. The first is called scalar multiplication, which you're multiplying a number, a scalar number with no direction, times a vector which has magnitude and direction. Okay? And this is called scalar multiplication. So to multiply a vector v, any old vector v, by a scalar c, any old number c, we multiply each component of v by c. So this could be c, that's a scalar, it doesn't have a symbol over it, times vector v, let's just call it v1, v2. Let's just imagine we're still in the plane, 2 space, 2 components. And you're going to multiply the scalar by those 2. Basically, it's just about like the parentheses suggest. You distribute the c on the inside. This would be a vector, and that vector would be cv1, comma cv2. Okay? That is scalar multiplication. Sorry about the sneeze, I'm trying not to. Scalar multiplication of any old number times the vector v1, v2. Now I say any old number. C is any real number. Positive numbers, that's going to scale it to be a longer vector in the same direction that v was. If v is here, and we're scaling it by some c that's greater than 1, then it's going to be some vector in the same direction greater than 1. If we multiply it by c that's between 0 and 1, then it's going to scale it back. It'll be in the same direction, but shorter. Okay? If we multiply it by c that's negative, then it flips it over and points it in the opposite direction, but along the same line. And if c is a small negative number, like between 0 and negative 1, then It's going to be a shorter vector here if C is a number magnitude greater than 1, but in the opposite direction, a negative number, then it's going to scale it longer in the opposite direction. And of course, if C is equal to 1, it's the same vector. If C is equal to minus 1, it's the same vector, but in the opposite direction. And if C is equal to 0, it's a 0 vector. Okay? So, some other characteristics. We'll get to those a little bit later. Okay. Oh, man. So one of the things I just said we're going to quantify here. So what if you have a vector v, just like we did below, but then we're going to multiply it by the number, scalar number 1. This produces a vector which is just often called negative v. Okay? In other words, it's that same vector v, but in the opposite direction. Okay? Same magnitude, absolutely opposite direction. Okay. Goodness gracious. My eyes are so dry I can hardly see. What about this weather? I can remember somebody, I can't remember when it was, years ago, I'd never heard this growing up, but someone called this, I think they called it blackberry winter. You get spring comes, it gets warm, you get comfortable and stuff, then you suddenly have a cold snap. And they called that blackberry winter. And I think it's because this is about the time blackberries usually start coming off, or at least the dewberries we used to call them did. Blackberries I think are a little bit later. And you just had a really cold snap then. In the fall, they have, you know, when it finally does get a little chilly, and then a few weeks later you'll just have an awfully warm week. I mean, it almost feels like summer's back again. They call that Indian summer. Why, I'm not sure, but so blackberry winter and Indian summer. That's, I think this is what they call blackberry winter. Man, it was too cold to have the doors open. I had the heat on driving in this morning, and I hung up my jacket last weekend thinking, finish with that for the season, and now I wanted to drag it back out, but I said I can manage it, because I think it's supposed to get up in the 70s today. So that may have something to do with my head being so wacko. I don't know. All right. Now, let's talk about subtraction of vectors. We just identified what negating a vector is. So, I think I'll go to a clean page here just in case we need it. And we'll probably, let me see, use it on here. Okay. What do we mean by u, vector u, minus vector v? We know what we mean to add vectors. What do we mean to subtract vectors? Say again? Okay. In some senses, you're absolutely right. In fact, I think exactly what you meant is, yeah. But here's one way to express that. That would be u plus the opposite of v, which is exactly what we do with signed numbers, isn't it? When we're subtracting signed numbers, you use the first, add the opposite of the second, okay? And we just figured out what minus v is. So if this is u, I'm going to use the same ones I did before. That's u. And this is v. Wasn't it about there that I did it? Something like that. And this is v. What is u minus v would be the vector u plus negative 1 times vector v. And negative 1 times vector v would be this here. Goodness, my eyes hurt. I'm going to hardly see to draw. That's why one reason they're so crooked lines. Okay, so this is minus v. And if you were to add this one to that one, basically do replace u this way, or replace v, a minus v this way, and this would be the resultant vector. Okay, u minus v. Now, to me, to do this geometrically, to do it with these parallelograms, the book is doing it, sure fine, not the easy way to do it. The easy way to do everything, I want to say, with vectors is to use components. Okay, so forget about the picture here, but that's really what's happening. What we do is just, as I think what Nigel was saying, you just subtract the components. Okay, I hope that's what he was meaning. In fact, I'm going to go back to now I'll do it here. Okay, I'll erase all things on the slide. Let v be negative 2, 5. I did it again. Imagine that's a parentheses. U equal 3, 4. Okay. Find each of the following vectors. The A part here says, what is 1/2 v? What would be 1/2 of v? Negative 1 would be the first component. 5/2 is the second component. Or 2.5 or 2.5 or however you want to express it. I would do 5/2, just like you did. Perfect. Negative 1, 5/2. Okay, the b from these would be what? U minus v. Okay, now, rather than drawing parallelogram, I would write down what u is. U is or you are? No, I'm just kidding. Okay, 3, 4 minus negative 2, 5. And if you just let your, what it looks like doing is what you're doing, that would be 3, 4 plus the opposite of this, which would be 2, negative 5. And then you add those two together, and what do you get? 5, negative 1. Okay? They show a picture of it as well, and I'll let you look at that. I'm probably not going to draw those, but there's 5, negative 1. The easy way to do it, just use components. Okay? How about 1/2 v plus u? Can you do that? Second, 1/2 v would be what? Negative 1, 5/2. That's what we did before. We already have that. Plus u, which is 3, 4. And what does that give us? 2. I'm sorry? 13/2 would certainly do it. Okay? Because 5/2 is 5/2, and 4 would be 8/2. 5/2 and 8/2 is 13/2. Okay? Got it. Okay, that's how the book did it as well. Now, they also had the picture, and I was going to do it, but there's just really no reason to do that. Let's look at Theorem 4.1. Now, I do know that the last time I checked, at least one person still didn't have a book. I don't know if he's gotten one by now. I kind of doubt it, but if he has, that's fine, good. let me write down these properties of vector addition and scalar multiplication in the plane. When you read that, meaning in two space, two dimensions. Here's U, V, W are vectors in the plane, meaning they each have two components each. C and D, scalars. Okay, these are vectors. And those two are your scalars. Okay. First property. Whole passel of them here. U plus V is in a vector in the plane. Okay, now, that has a name. That concept has a name that says that you have closure. I'm going to try to use the same phrases that I would have said it differently. Vector addition is closed, okay, is how I would have said it, but they're using it shorter. Closure under vector addition. I still want to put in that, vector addition. We already know that addition is closed in real numbers. You know, if you have a set of all real numbers, pick any two, add them together, you're still going to get a real number in the same set. This is saying that vectors in a plane, okay? Let's say that U is in the plane here and V is in the plane over here, okay? If you add those two together, you're obviously still going to have a vector that's in that same plane. Because if you have U and V and even W are vectors in the same plane, you add any 2 or 3 or 15 of them together, you'll still have a vector in the same plane. And that says vector addition is closed, okay? That vector, you have closure under vector addition, okay? Now, number 2, and I sort of indicated this one before too. If you add two vectors, U plus V, that's going to get the same result as adding V plus U, okay? And we saw that by our parallelograms. If you add U plus V this way and get this result, add V plus U this way, you get the same result. So these are, this is commutative property of addition. So this is commutative property of, and again, I like to call it vector addition because it is. It was true in scalars, but it's also true in vectors, okay? Doesn't matter which order you add two vectors, you're going to get the same vector sum, okay? Commutative property. And by the way, my silly way of remembering what this one is, I drove here from home to work. If I commute back home the same path, I'm doing it, you know, I'll just do it in different order. I started there, come here, now I'm starting here, going there. So I think of that, that's commuting. U plus V, V plus U, same. Fine. And that is the same distance here as, okay. Number 3. Not the same distance, but same distance and direction. Okay. Now, if you have two vectors, you add U plus V, and then to that vector sum, you add W. That's going to give you the same result as if you had started with vector U and add that to the sum of V plus W. And that's the associative property of vector addition. Okay, now, what does that mean in reality? Especially if you take these two and combine them together. If you have 3 vectors you're adding, it doesn't matter what order or how you add them, whether you add the first 2, the second 2, you always get the sum. Now, to prove this, component notation. Identify this as U1, U2, V1, V2, W1, W2. Add these two together because you just add U1 plus V1, and then you're adding W1, that would be plus W1, U2 plus V2 plus W2, that would equal U1 plus V1 plus W1, V1 plus W1. You get the same thing. So component notation is the way to prove these things as well as to work with them. Okay? Number 4. Pretty simple, straightforward. The U, or any vector U, added to the 0 vector, and we illustrated this before, that's always going to be the vector you started with. And again, and this is called the additive identity property. Okay? In other words, and again, prove it with component notation. This is U1, U2, plus 0, 0. U1 plus 0 is U1. U2 plus 0 is U2. Yeah, you're going to get the same vector at the end. The additive identity property. Now, almost sounds like the same, but it's a little different. If you have U plus a negative U, guess what you're going to get? The 0 vector, exactly. And that is the additive inverse property. Okay? Almost, I mean, they're similar here. Their names are similar, additive inverse property. You add a vector to its inverse, which is exactly the opposite of it, you're always going to get the 0 vector. Okay, and again, component notation would be the way to prove that one as well. So those first 5 are your additive ones. The next 5, 6 through 10, are your multiplication ones, and they almost go parallel. C times U, which is scalar multiplication of a scalar number times a two-dimensional vector, okay? That's equal to, well, that is in the same plane. It is a vector. I guess I should have said is then. Goodness gracious, this thing's a pain. Okay. Is a vector, goodness gracious, in the plane. Just like the first one. You add 2 vectors together, you're going to be in the same plane. So pick a vector U, multiply it by a scalar. A smaller scalar, a larger scalar, a negative scalar, a positive scalar, you know, whatever, you're still going to be in that same plane you were. In fact, you're going to be in the same line. But we're not saying that. We're just saying in the same plane. That's the closure under and I say scalar multiplication. Okay? They put scalar in there too. I'd like to put that in there. Don't just say scalar. Okay. Now, number 7. If you multiply a scalar times the sum of 2 vectors. Yes.
I know one thing is different. When we did Cal 3, we were doing vectors. They space all those out, be distributed like on down in one section, and the addition early in one section. They just do it all at one time and leave it out.
Yeah. Oh, you mean?
Yeah, we space it out, distribute property vectors in one
Right.
section, and then addition in another section.
Right.
And multiplication.
Right.
Yeah, they just do it all at one time.
Yeah. And I think this is sort of assuming you probably run into this before. So let's just review them all at once. Yeah. So yeah, you're right. Usually, and in some books they actually add to them. They'll do one and then say, well, in addition to this, you also have this. So then you have 2 or 3. Well, then we have this, and they finally get there. You're right. This one's just starting with the sum total. We may add a few more later, but this is most of them. What would this be?
Oh,
plus CV. That's curriculum vitae. No. And this, again, is a form of distribution. Now, you can't have a distributive property of addition because a distributive property combines addition and multiplication. So this is a distributive property, okay, and that's all they say here, distributive property. I like to say this, of a scalar over vector addition. Okay, because the next one, number 8, all they say is that's also distributive. And what this is you have two scalars, C plus D, and you're multiplying that by one vector V, was it? Or they use U. It doesn't matter. You could have used V. I'll go back and make it U. I'll make it U. Okay. Okay. What would that give you? CU. I see U. Okay. Plus DU. Absolutely. Okay. And that's also a distributive property, but this time it's of, really it's vector multiplication over scalar addition, if you think about it. Okay? Because you're adding two scalars multiplying by a vector. Okay? You could have put that vector in front, but usually you write the scalar before the vector, so they put it here. Okay? Number 9 is this one. Okay? Now C times DU is equal to the same as CD, which is a certificate of deposit, times U. Okay. Now this is a form of associative property. Okay. It's the associative property. Let's see. Put a few more letters there. Associative property of scalars times a vector. Okay. As long as two of these are scalars, then it doesn't matter which order you multiply. Okay? But we can't do anything with multiplying two vectors yet because we haven't even defined what they are. Y'all both know how to multiply two vectors. Two different ways. And we're going to get to that later in this section, out of this chapter. And finally, number 10, and we're almost at the end of time too, is very simple. The scalar 1 times the vector u is equal to what? U, okay? And that is the multiplicative identity property. Okay, good deal. Okay, that is where we're going to have to stop for today. Someone walked off with my pencil Thursday night, so I'm having to use another pencil now. So we will start, right there, I didn't even need it. Same place I started last time, there. Homework exercises here, I think you can do number 1. I know you can do 3 or 5 or both. 7 or 9 or both. 11, any of the odds 11 through 15. 17. And you can start working on some of the odds 19 through 23. And you could probably do more than that, but we'll do some more of those later. Okay? So, I didn't get as much covered as I wanted to today. We'll finish 4.1 on Wednesday. We'll talk about 4.2, vector spaces. Okay? I don't know if we'll get it finished or not, but we'll get as far as we can, and hopefully then we'll have enough questions for the test. What's that? I can't hear. Oh yeah, and it'll be easy though. Think of that. Okay. All right, we'll see you on Wednesday.